Today's topic is going to be a little bit different from what we do typically. We're going to use an interesting data set, in my opinion. It comes from the heart disease survey conducted by the CDC. And it's also a project on Kaggle, if anyone is familiar with this portal where you can find a lot of machine learning competitions and different kinds of data sets. So first of all, I will try to give you a conceptual overview of what we are going to try to do today and how, and then we'll kind of dig a little bit deeper into the actual methods and how you can probably get started with this kind of analysis, keeping in mind that the same approaches are going to be useful not only for this kind of data, but really any kind of data that you come across. Now, what is different about this particular data set from the typical data sets that you will find on the portal, for example, is that this is a survey. And the survey is typically not numeric. So we'll talk a little bit about encoding. It is also different from omics data. And a lot of times you will find these tutorials on our portal, for example, for transcriptomics data or metagenomics data or other structured data sets. And they have a very specific property, omics data sets do. The property is that the number of samples is much less than the number of features. And in this case, it's the other way around. You have a lot more samples, individuals, and less features, less questions that are being used in this analysis. So without further ado, let's get started. So what is heart disease? Heart disease is the leading cause of death of men and women since 1921. And it is, together with stroke, accounts for about 40% of all deaths. One person dies every 36 seconds in the US from heart disease, which means that during this workshop, a number of individuals are going to unfortunately pass away. And not only that, this disease also costs over 360 billion last year, which means that this is a very expensive problem to treat. Now, to understand how we can address this pressing and significant need or burden, we need to try to understand what kinds of factors lead to heart disease, or what are typically the lifestyle behaviors or predispositions, such as diabetes, that actually leads to heart disease. So we hope that the goal of this workshop will be twofold. Number one, know that there's a high risk of every one of us developing heart disease, and we need to be aware of what those risks are. Number two, you will be able to use data from a significant, sizable representative population to know that it's not only for you, but for people around you as well. What is this data set? So this is the 2020 annual CDC survey, which has about 400,000 adults in the US. And the survey was conducted to identify health factors that are common among people that have heart disease. So there's two major groups. There's people that have heart disease, and there's people that don't have heart disease. And by comparing them, we can find interesting patterns. What types of features or observations do we have? Well, obviously, we have heart disease, yes or no. So people that have coronary heart disease or myocardial infarction are the people who are considered to be with heart disease. And then people that don't have those two conditions don't have heart disease. Then there's BMI, which is the body mass index, which takes account your size as well as how much you weigh. So it's kind of a proportionate measure. Smoking, which in this case, if you have smoked at least 100 cigarettes in your entire life, you are considered to be, a smoker. So it doesn't mean that you're actively smoking today. Alcohol drinking, heavy drinkers, so adult men have more than 14 drinks per week, or adult women having more than 7 drinks per week are considered to be yes for alcohol drinking, or if you have less than that, then you're considered to be no. Stroke is if you ever had a stroke in your life. Physical health, how well you move, but also your physical illness or injury. And this is a subjective kind of an evaluation that you evaluate on yourself. Mental health, so what again could it be in the past 30 days? Difficulty of walking, if you have serious difficulty walking or climbing stairs, sex, or male or female, and then different types of age categories. So all of this data, there's a lot more data to the actual data set. You can find the full data set on the CDC website. But what we are going to be doing is we're going to take a cleaned up version of this data set. In other words, something that was a little bit curated and adapted for the needs of data analysis. This cleaned up data, again, this can be found on Kaggle, but this cleaned up data, as you can see, is standardized, right? And so because it is standardized, now we can kind of try to see what are the proportions of individuals in the survey altogether that fall into different categories based on these different features. For example, people that do have heart disease are only 9% out of this population, and people that don't have heart disease are 91%. What does that tell us? That actually points to the main point of today's message, and the main point that we want you to take away from this workshop today is that this is a highly imbalanced data set. And imbalanced data sets introduce a specific challenge for machine learning, right? Because we have so many examples of people who are kind of in the no category, right? They don't have heart disease, and a much smaller representation of people that do have heart disease. And because, as we all know, individuals are very different, even though they might have or not have heart disease, all kinds of other factors could change significantly. We have less information to train our model using this kind of data about heart disease individuals than individuals that don't have heart disease. And that is a challenge that we're going to try to look at. Now, the analysis objectives, or the objectives from this workshop for you, we hope that you will be able to, number one, understand how to deal with public health survey data. Surveys are a common way to try to evaluate different risk factors and different things that you can study about the population, but we'll see how effective these methods are and what are some considerations that you should have when you deal with survey data. Number two, we'll talk about the role of exploratory analysis and how it's useful and what kinds of insights you might get from what's called exploratory analysis, or summarizing the data and exploring different patterns. We'll talk about different types of machine learning, and we'll talk about supervised and unsupervised methods like clustering and classification, but we'll also talk about when and how they are useful and why would we use one or the other in a specific situation. We'll then talk about specifically about different methods of clustering. And I think this is also important here because as we look at the data and we look at how this data could be summarized, we'll see how different methods of clustering are more or less useful to discover patterns and noise in the data that we have. Then we'll talk about how to perform clustering, evaluate clustering, and how to apply classification and evaluate classification. So important kind of concepts for anyone who is going to rely on machine learning to draw insights from data analysis. And then we'll specifically talk about this challenge for unbalanced data. What kinds of methods do we have to make sure that the training and the test and the validation are actually possible, even though our data is biased, right? It is not representative of an equal kind of proportion of each category. And here you have, I think, an image that summarizes it well. We can imagine that this is a principal component or some kind of a two-dimensional plot that actually shows us these two different groups. Let's say 0 are people that don't have heart disease and 1 are people that do have heart disease, right? And you have a clear distinction between these two groups, but nevertheless, it might be challenging to draw the exact line between them because there's overlap. And because there's this overlap, immediately you might start thinking, well, who are the people at the intersection, right? Are these people that could have heart disease, but they're actually not classified as people with heart disease? For example, they never went to a doctor to determine this condition. Or maybe there are people that do have heart disease that are not that sick, right? Maybe they had heart disease, but they fully recovered, right? And then how can we take these kinds of insights and kind of develop some ideas or hypotheses that we could actually test and discover specifically in a data set like this? Now, we are going to use Python in this particular workshop, even though you could use R and you could use even Excel for some of these things. And there are many different tools out there that you could actually use to perform such analysis. But in the context of the limited time that we have together today, we hope that you will get a pretty solid introduction to Python and one important package in Python called sklearn or scikit-learn, a package that is going to be very useful for anyone dealing with conventional machine learning applications and evaluation. We'll also talk about two different methods of visualization, matplotlib and plotly. Matplotlib is actually a very useful library of visualization, a library that is embedded into sklearn and made very useful and user-friendly, I would say, for anyone who is used to coding with Python. And plotly is a specific package that is used for interactive data visualization. So we'll see how this interactivity helps us extract more insights quicker than when we use more static visualization. Finally, we'll talk about several different specific data science tools that you will be exposed to today. We'll talk about encoding. So as I mentioned, this is a data set that contains such answers like yes or no, right? And so we obviously want to convert those to integers because most machine learning methods are designed to work with numeric data. So we'll talk about different kind of approaches to encoding. Correlation analysis. Ultimately, relationships between data sets and numbers could be measured in different ways. And we'll talk about one of those ways, which is correlation. But we'll also talk about variance. And that is a feature that is going to be used in the principal component analysis part of today's workshop. Then we'll talk about different methods of clustering, kind of standard low-dimensional methods like k-means and hierarchical clustering, and a little bit more advanced density-based methods like dbScan. We'll then talk about different approaches to classification and why we have different approaches to classification. Many different methods exist, and we'll kind of learn about two approaches, SVM, or support vector machines, and random forest, a variation of decision trees. But we'll also briefly touch on this aspect of AutoML, right? How can we kind of test many different approaches and find one that works best? And then finally, we'll talk about the specific objective of today's workshop, which is to try and work with our model to make it more balanced. And how does that affect the outcomes, right? Our ability to get a better, more balanced training and test data sets so that we can get better insights. Now, before I jump into the topics that I just mentioned, let me briefly mention that this is a part of the OmixLogic data science training program. So as Sonalika already mentioned, we have a lot of asynchronous resources as well as a mentor-guided program that you can participate in that will allow you to gain hands-on skills and exposure to a variety of omics-based data science projects that you can leverage to improve your career. And we hope that anyone, if you have a background in biology, biotechnology, medicine, or others, would be able to gain those skills as well. And that is why we made a lot of those tools easily accessible. We've made simple to follow tutorials, and we allow you a whole set of features to perform the analysis, but also develop a project of your own using our portal called OmixLogic. Now, on this portal, you will find these practical step-by-step tutorials that will cover most of the things that we will speak about today, including how to load data, manipulate, visualize, and analyze your data using statistical methods, perform dimensionality reduction, and so forth. So most of the topics that we cover today are going to be also explained in a very step-by-step manner inside of these courses. And there you will find courses both in Python and in R, as well as user-friendly methods, for example, methods on the T-Bioinfo platform. In addition to that, you will find curated data sets. So today, we're using the CDC heart disease data, but there you will find other interesting data sets, such as modeling cancer precision medicine, or analysis of the Cancer Genome Atlas, liver cancer risk evaluation, and many other examples as well. Okay, so before we go on, does anyone have any questions? Let me check the chat box. Okay, so someone is asking, I wanted to know whether you have any portal for peptide design as therapeutics in your courses. We actually have a very specific program designed specifically around structural biology. So please share those links in the chat if you may, specific to virology as well. So Sonalika, maybe you could add that information in the chat. We will have this webinar recorded, so you're welcome to review the webinar recording after we are done. So I see some question about that. And I see other people that are saying, I'm interested in translational oncology. So that is great. So if you're interested in oncology, as I mentioned, we have a number of projects. And those that are interested in precision medicine, precision oncology, any kind of molecular data, this is exactly kind of the emphasis of our training typically. And I do want to mention that we have a variety of programs, projects, and resources that you can leverage for that. Another person is asking, please put emphasis on what these different analyses signify from a qualitative point of view. I will make sure to do that as well. Will there be a .py file given to us at the end of the webinar? Well, actually, we will have a full interactive notebook for you to follow. So we will share that momentarily. This is an introduction to give you a high-level overview of what we will do. And then Raghav is going to be able to take you through the practical things as well. So Nalika, as I mentioned, if you could share the links to the different programs that we have about oncology and precision medicine, that would be great. And let me just very quickly find Dr. Raghavendran, who will be presenting soon. But first, I will finish my part because I think it is important to have a good understanding of what we're trying to achieve, right? What are the actual insights? Okay, so let me briefly go over these topics before I pass on. I know that everyone is excited and waiting to get hands-on working with the data, finding all kinds of interesting patterns. So what is the objective of this kind of analysis? So any kind of a data science project is separated into three major steps. So at first, somebody collected the data. That could come from an experiment, that could come from the real world, right? This survey comes from the real world. These are actual individuals that were surveyed. And based on where the data is coming from, you should have an appropriate kind of assumption about that. Once you get that data is processed, right? And processing can mean many different things. In the case of omics data, for example, that means maybe compiling all of the bits and pieces of information into a single table. In this case, we will look at, for example, one-hot coding, encoding of different methods. So you have yes and no, you can convert that to integer encoding. You have multiple categories, you can convert those to multiple levels, and there's many different ways to do that. Another issue could be raw data might have missing values, right? So how do you eliminate those, or how do you fill those in? So cleaning that data, organizing that data, and structuring that data typically is that processing step. Then we have the step of exploratory analysis. And exploratory analysis is really asking the question, what kinds of patterns pop out? So what kinds of patterns could pop out at us? We could find distinct groups or patterns or abnormalities, anomalies in our data. That is a part of exploratory analysis. How can we find those? Well, we can find those in two major ways. We can visualize our data using different standard tools like proportion, right? Or statistical features like variance. We could also mine our data, right? We could look for more discrete and kind of interesting patterns in our data and visualize them. So it's really a back and forth between visualization and data mining. After we have performed that, typically what we come to are some well-defined questions. For example, if I have people in the heart disease category and the no heart disease category, how many of each categories have been smoking or using alcohol? And is there a statistical difference between those two groups based on these observations? And that is called statistical modeling. And this means that we are trying to find a significance that is representative of the population. And that is called inference. So we're actually trying to infer from the population that we have something that could be generalized about everyone, right? So here we have 400,000 individuals, but we have over 3-4 billion people in the world, or maybe even more now. So how can we look at this population that we have surveyed to generalize and find some universal pattern that we think is consistent for everyone across the board, right? And that would describe this general topic of a disease, right, like heart disease, and these generalized topics of smoking, drinking, BMI, and other health patterns. All right, now let's briefly talk about Python. So Python is a very useful and I would say a user-friendly language to use in your analysis. It might seem difficult for people to get into it, right? So I want to briefly speak about this and explain why Python is a worthwhile investment, number one, into your skills and your career. For those of you that already know Python, you can pretty much skip these next few slides. But if you're new to Python, I want to make sure that it is very easy for you to get started, right? And I don't want anyone to think that, oh, this is going to be a lot of coding and I'm going to struggle. I don't think so. I think you'll find it enjoyable. We'll try to make sure that every aspect of what we do is clearly explained. And if you have questions or would like to learn more, we have a series of tutorials and guided programs as well that can help you gain those skills and use them in the future. So two specific things that you need to know about Python. Number one, Python is user-friendly because it has a lot of packages that people have designed to make things easy for you. For example, there's a whole package of functions in NumPy or Pandas that deal with the structure of data. And so we'll use a lot of those to be able to prepare the data for our analysis. Let's now talk about exploratory data analysis. So how can we look at this particular data? And again, you will jump into the hands-on portion in just a few more minutes, but so that you understand each stage and what you're expecting to get out of that stage, let me give you an idea of what you will find. So first of all, exploratory data analysis, as I mentioned, is just to ask simple questions, right? How can my data be divided into groups? And what can those groups tell me about the different population members or representatives that I have here? As we mentioned, there's about 9% of people that have heart disease and about 91% of people that don't have heart disease. And that makes it an imbalanced data set. There's about 60% smokers and 40% non-smokers, and about 93% alcohol consumers versus about 7% people that don't consume alcohol. In addition to that, there's 96% of people that had a stroke and about 4% that did not have a stroke, right? So this just gives us some statistical understanding of categorical variables. And you can see that probably if we have people that are 91% heart disease and 9% without heart disease, there's a big overlap between people who are smokers and non-smokers, which means that there's a lot of non-smokers that have heart disease, or there's a lot of people that are smokers that don't have heart disease, right? So these are kinds of questions that we can start thinking about as we look at these proportions. In addition to that, you can look at other kinds of things here as well. So you can change, for example, how you visualize yes or no, right? And you can say, among people that have heart disease, how many of them are smokers? So it turns out that 60% of the people that have heart disease are non-smokers, or 84% of the people that have heart disease also had a stroke, right? Or 66% of the people have heart disease and they are diabetic, right? And this is an interesting way to look at it, because you see that, for example, well, 16% did not have a stroke, right? Or 4.17% don't consume alcohol, right? So there's a proportion of people. Now, if you think about it, 4% of 400,000 is still a significant number of people. So there's a lot of people out there that don't smoke, don't consume alcohol, have not had stroke, and don't have diabetes, but yet have heart disease, right? And that's why it's not just a very simple way to interpret the data just by saying, oh, well, there's a lot of people that drink alcohol that have heart disease. It must lead one to another. I mean, it probably does, but it's more nuanced than that. There's more variation in our data. And that's what we are finding as we explore the data that we have. In addition to these categorical, simple categories, we also have numeric variables. For example, BMI is a number, right? And that number is on a continuous scale. So it can go anywhere from 0 to maybe 100. And what you can see here is a histogram, a distribution of values in each category. And so you can see that, you know, this is not to confuse with the numbers of people. So the y-axis represents how many of those people we have in each bin, right? And so you can see that the distribution is fairly normal, right? That's the kind of outcome from here. And the reason you have a much lower red than blue is just because you have so less people in each category, right? You just have 9% of the people are in the heart disease category, whereas 91% are in the no heart disease category, right? And that's why this might be a little bit confusing if you just look at it. Now, why in the world would we use principal component analysis to perform this exploratory analysis? And so here, briefly, I'll explain what principal component is and why it's useful in this category as well. Well, principal component analysis, if you look right here on the right side, basically tries to find such components in the variance covariance matrix that maximize variance of all of our data, right? So I'm trying to kind of find such projections in my data that would explain variance for all of the data or the majority of the data that I have. And there are several things to remember here. Number one is that this is very useful for visualization, but not very useful for actual conclusions about the data, because it doesn't give us a lot of statistical confidence in what we are saying. It just shows us different patterns. Now, when we have complex patterns, it's very useful to explore what those patterns are, because we're looking here at some kind of reduced dimensionality of the actual data set, right? So we're like looking at the shadow of the real object. And as you can see on the left, when we add multiple dimensions to this visualization, it starts showing us interesting patterns. For example, in this PCA, I actually see 4 different groups, right, that have different patterns inside. You can almost see it right there, right? Different patterns right here, right? It's kind of visible, right? I have 1, 2, 3, and 4. So that means there might be some batch effect, right? Something that I might want to look into more. Like, let's say we have, our age group separated into 4 categories, maybe that's what those groups are, right? And so I could explore how that impacts what I am going to get in terms of getting all the data. And one additional insight that that could give you is maybe we could separate our data into different groups and explore them separately if we want to get better results. So a lot of this analysis actually is done so that we can find significant variables, features, right, that could be statistically significant in our analysis. And in this case, one way to check, a quick check for some relationship is to build a correlation matrix. So everybody probably knows what correlation is. Correlation means that if one number goes up, the other number also goes up. And it's a fairly linear relationship. So a correlation could range between 0 and 1. And in this case, when we build this correlation matrix, you basically see that most of these values are uncorrelated. And maybe the top one is the difficulty in walking and physical health, which is a very intuitive kind of a thing, right? So you can see that physical health, which is how you move, and difficulty walking should be correlated, right? And so those are the quick insights that you can get from here. In addition to that, you can get your typical statistical kind of evaluation of each one of your numeric values, like BMI, physical health, mental health, and sleep time. So here you can see also age category is associated with higher chance of heart disease, difficulty of walking, and skin cancer. Interesting. Physical and mental health are slightly correlated, right? That means that for some people, physical and mental health are kind of going together, right? And so I think that is also expected. All right, now, as I mentioned, we go from exploring our data and kind of understanding what is in our data to trying to define specific groups within our data that we can cluster together, or we can say these are defined groups that we want to take a look at further. So let's say we have our principal component analysis, as I see on this side. And here I want to now say, I don't want to just color them by different colors. I actually want to define them. And definition could be done by several different methods. But the objective of those methods is pretty consistent. The objective is to say that this is my groups, and this is the borders of those groups, or maybe these are the specific relationships within the group, right? So how could I evaluate my clustering? I could actually start saying, well, how many clusters do I expect there to be? And what if I give that number are the measurements within and between the different clusters? And that will give me some conclusive analysis of my data. So in our specific case, what we're going to do is we're going to use several different methods. This is an algorithm of one of those methods that is called hierarchical clustering. And hierarchical clustering basically takes a number of points and measures Euclidean distance between them to organize each group of dots or objects, in our case, individuals, into bigger groups. And it will perform that bottom up, so from each individual in our data, all the way to one single group. But in reality, there are many different types of methods of clustering. And so in the context of today's workshop, we'll explore just a few of them to get a sense of how different they are and how they use different metrics and settings that could be appropriate for this specific use case. So we'll use that, we'll look at methods like k-means, Birch or agglomerative hierarchical clustering, and we'll look at density clustering as well, in particular dbScan or density-based scanning clustering. And there are some other ones like grid and model, etc. We'll not go into those today. So one important thing when you deal with methods of clustering like k-means or hierarchical clustering is that they kind of ask you from the beginning, well, how do you define the number of expected clusters, or k? And you can say any number. I expect 2, I expect 4, I expect 24. How do you determine where is that cutoff and what's the appropriate number of clusters? So we'll look today at the elbow plot, where we'll use the silhouette measure to determine the number of clusters. And you can use the silhouette or the inertia for k-means to find that optimal number or range of numbers that is appropriate for a data set. Ultimately, once you have performed such clustering, you can see right here is the result mapped on the principal component, you can start asking specific questions, right? For example, in the first cluster, or cluster number 0, I end up with 99% heart disease and about 1% not heart disease, right? And so maybe this cluster is specific to heart disease. And here I can see proportions of other types of variables that I might be interested in. I also have here other kind of comparisons within other clusters. And here I can also look at, well, how many samples got assigned to a particular cluster. But ultimately, I'm also interested in the separation between my clusters, and I see that the separation is actually not that great. And that's why, in many cases, we want to use many different methods of clustering, because each method of clustering has an application to more complex data sets. So here you can see this is k-means clustering. This is a hierarchical clustering, the way it works. And here's dbScan. And so you can see that dbScan can actually work with more complex patterns that maybe a more simple method like k-means or hierarchical clustering might have difficulty working with. And so we'll look at several of those methods and think, how are they useful in this example? Finally, we'll talk about classification. So what is classification? Classification is when I want to assign some group of samples that I have to a class, and then think, how can I train a model to recognize those examples in an unlabeled data set, in a test data set? What's important here is that I can do it with simple rules, right? Just like we saw in clustering, I can say, well, if you have heart disease, and if you're a smoker, and if you had a stroke, then you are more likely to fall into the heart disease category. Now, that might be a very simple way of doing that, and depending on where I start from and where I end, I might get several different results. So that's why we will take a look at more advanced methods like random forest, which is essentially the same idea, but many different times on several different bags of data within my data set. How can I get better results? So here we'll talk about how do we train a model? How do we do bagging and bootstrapping? And then finally, how do we evaluate the outcome of our training? And here we can look at several different parameters such as accuracy, precision, recall, the area under curve, and importantly, we'll take a look at the F1 score, or the method to evaluate how well our model performed, even with the imbalance that we might have in our data. Ultimately, we will take a look at going from a very good model that has high accuracy, over 90% precision, but nevertheless a pretty poor F1 score for one of our classes, or the class that actually has heart disease, which is what we are interested in. We'll also look at how to, once we have fine-tuned, and kind of made a good model and tested it, how can we use it to evaluate feature significance, or how different features contribute to our ability to classify that particular condition. And ultimately, we'll get to our balancing of our model, and how can we use balancing to get a better model that could be even further refined if we start taking apart this data set and looking within individual cohorts.